Our first keynote speaker, Nield, who will be talking about the role of glacial isostatic adjustment in Earth structure on ice sheet and sea level evolution.
Thank you very much. Thank you so much to the organisers for inviting me to talk to you today. I'm going to speak about glacial isostatic adjustment and hopefully set the scene a little bit for the rest of the day. So, glacial isostatic adjustment describes the response of the solid Earth to changes in ice sheets at the surface. So, as an ice sheet melts, we see an immediate elastic response of the solid Earth, much like if you were sat on one of these, well, we call them space hoppers, I don't know what you call them elsewhere. If you sit on one of these and get up, it immediately responds and regains its shape. Over longer timescales, we see a prolonged viscous response of the underlying mantle as mantle material moves back to the formerly loaded regions. And this leads to processes such as surface deformation, sea level change, shoreline migration, changes in the gravity field as mass is redistributed through the system, and rotational feedback. And how long this process takes depends on the underlying viscosity of the Earth and the size, the shape, and the deglacial history of the ice sheet. So, for example, in some regions of the world, such as Fennoscandia, we're still seeing rebound from deglaciation from the last glacial maximum. If we want to predict glacial isostatic adjustment, quite often we use what's known as a forward model. The two main inputs to a forward model are the ice history and the Earth structure. The model then predicts outputs such as Earth deformation, sea level change, and gravity change, which we can compare with observations. And these two inputs are essentially tuning dials, so we can adjust each one of these until our model predictions match our observations. However, what these traditional forward models don't take into account is the feedbacks between the ice sheet and the solid Earth. These solid Earth ice sheet interactions can actually affect ice sheet behaviour, and we saw this presented several times yesterday. Here's a figure of an ice sheet on a reverse bed slope. The grounding line is the position at which the ice sheet starts to float, and mass loss is governed by the ice thickness at this point. The grounding line position also depends on the local water depth. So looking at the ice sheet in isolation, if that starts to melt, what we see is grounding line retreat into deeper water depths, and flux across the grounding line increases. But if we take into account GIA feedbacks, what happens is the melting of the ice sheet triggers land uplift and a local sea surface fall. And this decrease in local water depth acts to stabilise the grounding line. Flux across the grounding line decreases and the system is stabilised. We also see a flattening of the slope, which reduces basal sliding within the ice sheet and alters the internal forcing. And changes in elevation of the surface can affect surface temperature and rate of accumulation and ablation. So whilst our GIA response is governed by ice sheet evolution, at the same time, the deformation of the Earth can affect how an ice sheet might grow or decay. And this is particularly important for marine-based ice sheets, such as the West Antarctic ice sheet. To fully understand the solid Earth ice sheet interactions, we really need to know what the underlying Earth structure is. And in this next part of the talk, I'm going to speak about how we might find that out and some of the main advances in GIA modelling. In a traditional GIA forward model approach, the Earth is represented as a 1D Earth. So this means that the Earth's properties vary in the radial direction only, and quite often limited to 3 layers. So we have an elastic lithosphere, a lower mantle, and an upper mantle that have one consistent viscosity. This is paired with a Maxwell rheology, where we have an immediate elastic response and a longer-term viscous response. And this viscous deformation is linear through time. Typical values for a global average upper mantle lie in the range 5 times 10 to the 20 to 1 times 10 to the 21. However, in regions where we see lower viscosities than this due to the tectonic environment, these 1D models don't accurately capture deformation with these kind of global average values. So how can we find out what the underlying Earth structure is if we want to move away from these 1D simplified models and towards a more representative representation of the Earth? We can have a look at regional 1D studies where we fit forward models to local observations. Geological evidence such as raised shorelines and sea level indicators can tell us about the Earth structure as well. We could use the adjoint method where Earth properties can be inverted using gradient-based optimization, and this is slightly different from the forward model. Seismic tomography is a really good way of finding out how properties vary laterally within the Earth, as shown in the figure. And we can also look at constraints from other disciplines, such as post-seismic deformation. So now I'm going to show you 3 examples from the Antarctic Peninsula to illustrate these different processes. So starting with a regional 1D study. So in 2002, the Larsen B ice shelf collapsed, and the glaciers feeding this former ice shelf started to speed up and lose mass. This mass loss was accurately captured in ISAT and DEM differencing. And this large amount of mass loss triggered a solid Earth response that was observed at the Palmer GPS station, which is located just on the west, just over here. Luckily, this GPS station was operational both before and after the Larsen B ice shelf collapsed and captured really nicely the increase in uplift, which started around 2002. It was initially hypothesized that this was a purely elastic response of the solid Earth due to the short timescales. However, when we did the modelling, it was clear that the model predicted uplift just from a purely elastic model wasn't anywhere near enough to reproduce the observations, even within the upper and lower bound. And actually, we needed 4 times the amount of ice mass loss to get anywhere near the observed uplift. So we ran a viscoelastic model and tested a whole suite of different Earth properties and different mantle viscosities. And what we were able to do was to constrain an upper mantle viscosity of around 10 to the 18. And this was significant because it's the first time that viscoelastic deformation was captured by observations on this timescale. The second example from the Antarctic Peninsula is from relative sea level records from this study by Alex Sims in 2018. They dated raised beaches from Torgerson Island, which is located around 1 kilometre from Palmer, which is the GPS I showed you in the previous slide. These late Holocene relative sea level records indicated substantial variation in solid Earth uplift rates over about the last 1,000 to 1,500 years. And this suggests that the Earth is responding to recent local changes in ice loading rather than deglaciation from the LGM. If it was deglaciation from the LGM, we would expect the uplift rate to stay constant through time. And this is further support for low viscosity in this region. The final example I'm going to show you from the Antarctic Peninsula is from post-seismic deformation. So post-seismic deformation is the viscoelastic response of the solid Earth following an earthquake. The sudden large, the sudden large stress change associated with an earthquake triggers viscoelastic response of the lower crust and upper mantle. There was a large earthquake that happened just here at the boundary between the Scotia Plate and the Antarctic Plate in 2013. And this was captured in a GPS record from right at the tip of the peninsula. At the time of the earthquake, there's a clear co-seismic offset. This is the immediate displacement at the time of the earthquake. And then following that, we saw post-seismic viscoelastic deformation in the GPS records. So using the same forward modelling approach, we ran a model of post-seismic deformation with a whole suite of Earth models and different Earth structures until we found our statistical best fit model, as shown in the blue. This time what we found was that the observations actually preferred a Berger's rheology. So a Berger's rheology is slightly different than a Maxwell, and it has two different viscosities. We have an initial transient viscosity and a longer-term steady-state viscosity as well. So these values for our preferred model go as low as 4 times 10 to the 17 for our transient, which acts over the few months following the earthquake before it settles into a steady-state deformation. So what is the mantle viscosity below Antarctica, and how can we use these individual studies to help? This is the ANT20 seismic velocity model, and what the seismic velocity models can really nicely tell us is the lateral variations in Earth properties. So you can see East Antarctica is dominated by blue, so this indicates denser, colder and higher viscosity material in this area. Over in the west, there's large regions of red, indicating less dense material, hotter and lower viscosity. And what we can do is use these regional studies that have constrained Earth properties to calibrate this seismic tomography model. So the seismic tomography doesn't directly give us viscosity, but gives us relative differences. And we can use these values constrained to calibrate that. So there's an increasing number of these studies from particularly West Antarctica. And what's clear is that they're all 1 or 2 orders of magnitude less than the values constrained using a 1D average model. Just going to do a shameless plug for my own poster, number 30. I've been putting together these little bits of ice history to try and make a better GIA model for the peninsula, so do come and talk to me about that later, if you're interested. So in addition to thinking about how viscosity varies in space, we might also want to think about how it varies in time. I already mentioned the Maxwell rheology, where viscous deformation is linear in time. This really well captures what we call long-term GIA, so GIA that's acting over several thousands of years, for example, from deglaciation from the LGM. But in these regions of low viscosity around West Antarctica, there's the question of whether this Maxwell rheology is still suitable. And we might move towards something like Berger's rheology that has both short and long time scale viscosities. There's also rheological flow laws that have been derived from lab experiments on rocks, and these take into account more of the local tectonic and deformation environment parameters, such as the grain size and water content. This is a bit of an emerging area of research in GIA. There's several studies that have been published on this already. This one from Karen Simon particularly states that transient deformation resulting from a Berger's model might better explain rapid sea level drop that's observed in sites underneath or adjacent to former ice sheets. And this is an important result. When we're thinking about how to interpret observations. So these two emerging areas of research, of 3D modelling and different rheologies, do come with their challenges. They're quite computationally expensive. Models take quite a long time to run. We're introducing many more unknowns in the parameter space as well. If we just go from Maxwell to a Berger's rheology, we're then immediately trying to constrain 2 different viscosities rather than 1. And often we don't have the observations with which to do this. We're still lacking a lot of information about ice history, which is our other main input to a GIA model. And there's quite often non-uniqueness and trade-offs in the GIA solutions. One thing that can really help us address these challenges are the GPS observations of Earth deformation from around Antarctica. And there are several networks in operation around Antarctica currently. So I've shown that these GIA feedbacks are important when thinking about the ice sheet, but how can we include them in ice sheet models? The most simple approach to this is using the ELRA model. This stands for Elastic Lithosphere Relaxing Asthenosphere. It's quite a simple approach to incorporating deformation, but doesn't include GIA. So there's no sea level changes and there's no changes in the geoid. The Earth is represented with one constant relaxation time, so it's essentially a 1D model. But the benefit of this is that it's very efficient and it's already coded into a lot of open source ice sheet models such as PISM and Glimmer. There was a study in 2021 from Coulon et al. Who improved on this by including essentially a spatially variable ELRA in their model. So they had different relaxation times for East and West Antarctica, reflecting the different Earth structures there. They also included an approximation of the gravitationally consistent geoid and near-field relative sea level changes. And then they compared results for grounded ice volume when no feedbacks were taken into account and feedbacks were taken into account. And projecting this 5,000 years into the future, you can see differences of around 2 meters of equivalent sea level between when no feedbacks are included and the geoid and solid Earth feedbacks are included. And this is because the GIA feedbacks significantly promote the stability of the West Antarctic ice sheet. So moving on, excuse me, to a slightly more complex model. This is a 1D coupled ice sheet solid Earth sea level model. And this figure is from Whitehouse et al., but the model is from the Gomez group. Over the past 40,000 years, we can see that the ELRA model predicts up to 7 meters of relative sea level change compared to modern, whereas the coupled model with a low viscosity mantle underneath reduces this to around 4. It's also particularly important for future projections. With no feedbacks, this keeps on increasing up to around 4 meters of global mean sea level equivalent, but with a couple model and a low viscosity mantle, peaks at about 1 before stabilizing. Going one further, with a 3D coupled ice sheet solid Earth sea level model, Gomez et al. 2018 compared the difference between the 3D coupled model and the 1D coupled model. They actually show quite a small difference between these two models over the last 20,000 years. However, there are significant local differences in ice history with the 3D model, particularly in West Antarctica, and this has implications for relative sea level. There's also another 3D coupled model that's just been published from Caroline van Kalkar, and that paper states that over the last glacial cycle, ice volume increases by 5 to 7% using a 3D Earth compared with a 1D Earth. Caroline's got a poster up this week, so do go and see her for further information. So I'd just like to finish with this slide, which nicely compiles a range of different estimates of present-day uplift rate from GIA. In the top row, we have Earth models that have a 1D Earth. There are 2 here with 3D Earth structure, a 1D coupled model, a 3D coupled model, and then the bottom row are estimates of GIA from inversion of geodetic data. And I think what's clear from this figure is there are still really large differences between these models, showing us that there's still a lot of work to do on both the ice history and the underlying Earth structure. So to sum up, solid Earth feedbacks can significantly affect predictions of ice sheet evolution, and this is particularly important for stabilization of the West Antarctic ice sheet. Coupled ice sheet sea level models show significant differences in projections of ice sheet volume and sea level change. Recent advances in GIA include constraining and including 3D Earth structure in GIA models, but that does come with challenges. Transient rheologies may be important and deserve to be looked at a little bit more in the future. A greater exploration of coupled models would also be beneficial, particularly for projections. For low viscosity regions, more constraints on late Holocene ice history are important, since this is the period of time that the Earth is responding to. We could do with some regional constraints on Earth structure for East Antarctica, and maintaining the geodetic networks of deformation can really help constrain GIA models. Thank you for your attention.
Awesome. Thank you. Any questions?
Hello. Thank you for a very nice talk. I'm intrigued by the Burgers model. Can you explain that a little bit more? How should we envision that, having like two viscosities? Does that mean more layers in depth or more spatial variations, or how does that work?
Yeah, so it's not really to do with the depth or spatial variations, it's more to do with the time evolving nature of the upper mantle. So this is more prominent when you have a very large stress change, so such as from an earthquake. You'll see an immediate, very fast response associated with an immediate low viscosity before the Earth kind of relaxes into a steady state deformation and a higher viscosity in the longer term. Does that make sense? It has two viscosities in a Burgers model. There's also the extended Burgers model that can have many layered viscosities.
I saw one over here.
My question was also related to this Burger rheology. So is the short-term viscosity could be related to the viscosity of the lower crust, or some short-term deformation present in the flowing crust? Or?
Yeah, it is usually the upper mantle layer that is responding this way. Yeah, where the biggest stress changes are.
Well, I have a local question about the Antarctic Peninsula. There is a rich subducted beneath the Antarctic Peninsula somewhere around 7 million years ago. And is it able to estimate, make some model of the uplifting of the continental shelf or the topographic response?
Yeah, so there was a slab subducted beneath the peninsula. Yeah, this has been picked up in seismic studies as well. What we did as part of the post-seismic study that I showed you is to make a 3D model where we simulated a slab underneath the peninsula. I think due to the small number of GPS observations that we have, we couldn't tell whether that improved the model really. There was no significant difference. But yeah, you're right. There are sort of more complex tectonic setting in that region. Yeah.
Thanks. I have a spectacularly ill-formed question. But if I'm thinking about the models that are used for sea level projection, I don't like the emulators or the intermediate complexity models. They don't have like a super realistic GIA. But they're tuned to mid-Pliocene warm period, sea level, last interglacial, and the observational record. So they're sort of, and those observational components would have obviously the realistic GIA in the physical system. So if they're sort of like tuned to those constraints, does it matter that they're not incorporating the GIA processes correctly?
I think for areas in between where there aren't good observations, yeah, it probably does matter. And the intricacies of the feedbacks in the system throughout the whole ice sheet model run can significantly alter the projections into the future.
Thanks, Grace. Nice talk. Just to help those who are struggling with the idea of transient rheologies, ice, of course, has primary, secondary, and tertiary creep phases, just like the mantle. And so you get transient responses in when you deform ice as well as the mantle. A question, though. This feedback on the ice sheet retreat has been known about for more than 10 years, and yet it's been very slow to pick up in many areas of the ice sheet modelling community. Do you have a thought about why that is?
That's a good question, Matt. Thank you. I think what that highlights is that we really need to talk to the ice sheet modellers. There are some ice sheet modellers who don't even want to acknowledge that GIA is important, full stop. So I think bridging those gaps with the ice sheet modelling community will really help us to move the models forward.
I'm just going to interject because I think that's gets to the core of why we're here. Thank you, Matt, for the question, and why we're bringing ice sheet modellers and earth modellers and atmospheric ocean people together. So I think the question's awesome because I've been wondering about this as well, and I guess I wanted to. I mean, I've talked to Natalia a little bit about the work she's doing with future projections, but. I mean, from a skeptic's point of view, does this get us out of trouble? and when can we see the first ensemble of projections that do include? Is it close in your community where you've coupled an ice sheet with solid earth?
Yeah, there are a few coupled ice sheet solid earth models out there. It's very technical and difficult, so there are only a few. I would probably default to those other people to answer those questions.
Awesome. Thank you so much.